Okay. So, coming back to the calculation of FM bandwidth, let us try to calculate that part. Suppose because it is FM, so what we will have to do, we already have seen that, that will generally any cosinusoidal whenever we represent with respect to the overall phase. So, I should represent it with a integration, okay, because whatever MT I will be giving, we have already seen that form, and it should be A cos some omega Ct plus integration of m alpha d alpha, right, into Kf. So, let us say that integration part I represent with another thing At. So, minus infinity to plus t m alpha d alpha. This is just for representation, we do not want to always write that integration form. So, we are just taking that as another function of t, because I am integrating up to t, right. So, then we define something, you will see why we are defining this. So, which we are not calling as phi fm, but phi fm hat. Why? Because I am defining a complex signal. So, I will define it like this, a e to the power j omega Ct plus Kf into At. It is very easy to see, if I just take the real part of this, I must be getting Fm, right. Real part of this will be e to the power j means it is cos plus j sine. So, I will get the cos part. So, that is Fm, a cos omega Ct plus Kf into At, where At is this one. So, that is Fm, we have already discussed that. So, I am trying to see what will happen to this, okay. So, I know that my phi Fm t, that Fm modulated signal, should be the real part of that, sorry, psi hat Fm t, right. This is something I know already in the background. So, let us try to see, I can write this as j omega Ct e to the power j Kf At, right, I can write it this way. Now, what I do, I expand this in an exponential series, okay, nothing else, and this I write as cos omega Ct plus j sin omega Ct, okay, you will see why I am writing this. So, I am just representing both of them in two different forms, nothing else. One is I am just taking Euler's formula, and the other one I am just putting the exponential series. So, this should be, first term should be 1, next term should be this j Kf At, right, divided by factorial 1, which is 1, then plus this square. So, it should be j square Kf square a square t divided by factorial 2, and so on, all other higher terms up to infinity, right. So, what you can see, every odd term, okay, wherever I am doing means this is probably the 0th term, this is the first term, then second, third. So, every in that way, if I just represent, every odd term will have means that will be a complex one, or I should say that will be the imaginary term, right, that j will be multiplied. Here it will be just j square, so I can put that as minus, okay. So, it will be like that, and I have this. So, therefore, whenever I write this, I can just take the real part of it, of this multiplication, right. So, that is something I can start doing. What I will see, wherever this j term is there, that should be multiplied with sine, and wherever there is no basically j term, that should be multiplied with cos omega Ct, that must give me this. So, therefore, immediately I can write phi Fm t from this understanding. I will just take all those multiplication where I will have real term. So, the first one will be a cos omega Ct into 1, the second term should be this multiplied by this, okay. So, that must be minus, because j square will give me minus Kf At, okay. So, that multiplied by sin omega Ct, right, and so on, right. There will be other terms like minus Kf square a square t cos omega Ct divided by factorial 2. So, this multiplied by this, and it will just continue, okay, as many terms are there which are free of j. all the real terms. So, that must be phi Fm. So, what I have done is I have got a expansion of phi Fm utilizing this. Okay. Carefully see, it has a cosinusoidal which is the carrier term. The next one is just like a DSBSC, okay, by AT, okay. That integrated signal whatever it is, that is as if you are doing a DSBSC. Of course, in DSBSC we do it with cos, but it is by sine, okay. But the spectrum will look like the same, okay. So, there will be a translation around omega c which will have a band which is equivalent to this band of AT, right. So, immediately you can see that at least FM modulation will have a band equivalent to that integration of this signal. Now, what we can also say, very carefully see, suppose this MT, that is a band limited signal, right. What do I mean by AT? That means MT is linearly passed through a integrator, okay. So, if MT is band limited, the integrated version also should be just band limited, because it is just it is getting passed through a linear circuit. So, if I just means this signal passed through a linear circuit, so what will happen? Wherever it is 0, there it will be 0. So, if it is band limited, wherever it does not have any component, it will also not have any component. So, if that is band limited, this should be also band limited with almost equivalent band most probably, okay. So, if that is the case, then I know that this is AT also will be band limited with equivalent band, because integrator is just nothing but 1 by j2 pi f, right. So, that is something we can just represent. So, if I just put that, immediately I calculate the band will remain the same, okay. So, AT in the frequency domain, if I try to see, that has equivalent band as MT or MF. If I do this modulation, so first two term if I just inspect, I have a carrier and I have already a almost similar like DSBSC modulation which takes the entire band. So, initially whatever we have said that FM probably might have 0 band, that is not true. From this analysis we can already see. But not only that, there are other stories to it. If you just start inspecting this one, this is also shifted at omega c. So, it is around omega c, but what is the band? It is having a signal which is square of A. So, it is a square t. What happens in the frequency domain? Whatever is multiplied in time domain, in frequency domain, suppose AT has a frequency domain or Fourier transform is AF. So, therefore, in frequency domain that should be convoluted, right. Now, we have already proven this, that two things convoluted, the band will be, if both the things are same. So, you convolute with itself, the band becomes twice, okay. So, this will have now 2B band and it will have all the higher order terms up to infinity. So, there will be a term where I will get A to the power nt, which will have n times the band and then n goes to infinity. So, what is the effective band of FM? That goes to infinity. This is when people started getting discouraged about FM. They could see that from the analysis it is very clear that FM band is infinite. So, whenever I do this modulation, because all the square cube terms, higher order terms of AT are being already embedded, okay. So, I am getting every frequency component getting populated by this, okay. So, that was one apprehension people had for FM, okay. So, this is, I hope this is particularly clear, right. So, I get infinite band, that is all right, but here there is a catch. Let us try to see that. If suppose this message signal is a regular signal which is bounded, let us say that is the case. So, what is AT? If MT remains bounded and it is a regular signal, then the integration of it also must be bounded. So, this is something we should be, because otherwise the signal means if the integration goes to infinity, then doing Fourier transform also is not possible. Okay. So, that is not a regular signal or any signal that can be handled in communication system, because that will not be possible. Okay. If we wish to calculate the power and all those things, it will go to infinity, right. So, or energy will go to infinity. So, that is that kind of signal, we are not expecting that kind of signal. Okay. So, basically what will happen, even the differentiation due to that or integration due to that reason will remain bounded. Okay. So, then I can always say this is bounded, this does not approach to infinity. I can then say Kf, which is a constant, into At, that is also remain bounded. Okay. So, this must be less than infinity, I can always write that. Okay. Now, a bounded value, what we are getting, the nth term if we try to inspect, it has Kf At to the power n, right. So, I have Kf At to the power n divided by factorial n. We know that this polynomial term does not grow as fast as this factorial term, that is true, okay, because we are in polynomial term, whatever we are multiplying, it is the same thing getting multiplied n times, where the factorial terms grows much faster. Okay. If that is the case, this is already bounded. So, this will grow faster than this one. Okay. Once I already know this, then I can say that as n approaches to infinity, this will approach to 0. Okay. So, all is not lost over here. What I can see, though I have infinite band, but the strength of that band, whichever is created at higher order term, it was going to infinity because the nth term was creating huge amount of bandwidth, n into that b, right. So, as n tends to infinity, this band goes to infinity, but what I could also see that the nth term as n goes to infinity, that gets vanished. So, basically the importance of that will be vanishingly small, and then I can conclude that most probably all these terms are not important. Some of those terms will be important, and with that there will be some band which might be bigger than of course b, that is something which is true, but it will not be infinite most probably. Okay. So, this is just an intuition that is coming directly from the FM signal analysis. Okay. We still have not proven anything about its bandwidth, we are just doing it just to exert something about the bandwidth. Okay. So, once we have this understanding, can we now go about analyzing the FM bandwidth? Okay. So, that will be our next task. So, let us say I modulate a signal which looks like this. Okay. So, this is my MT or MT. Okay. This is my message signal. I modulate this signal. Okay. First of all, probably we still have not proven that, we will resort to sampling theorem a little bit. So, we have not proven this particular thing, but we will just say that most of you, and later on we will also prove that, most of you know that this particular signal, as long as it is band limited, that means the bandwidth is less than b, then I have a effective Nyquist sampling, okay, which is 2 times of this one. Okay. So, 2b, if I just sample this signal, those samples are already representative of this entire signal. I do not have to really take, as long as it is band limited, I do not have to really take all the samples, infinite number of samples at every time instance. I can just sample it at an instance of 1 by 2b or even higher. Okay. The sampling rate at least has to be this. Lower than this sampling rate will not represent the signal faithfully. This is something we will prove, but this is the Nyquist sampling theorem. Okay. So, if I just sample it with this, I will just take these samples and those samples faithfully represent the whole signal. What does that means? I can actually start constructing box of that, of course, you can see because I have taken the box little bit bigger, actually it will come from the bandwidth of it. Okay. So, bandwidth actually gives all this slope. So, accordingly the bandwidth will be defined, and accordingly by sample size or this sample interval will be defined. So, this is not properly drawn. Means if I just plot this into frequency domain, I will see probably much higher frequency terms are there because of this variation, and due to that 1 by 2b will be much smaller. But whatever it is, there will be a 1 by 2b which faithfully represent it, and then I can just take those samples and I can make this sample top flatter. Okay. So, I will say that that particular flat sampled signal, whatever I am this box, if I just put one after another, whatever I get, that actually faithfully represent this signal. I am not saying any wrong thing over there, because I know those samples are true representative of that whole signal. We will be proving that also, sampling theorem says that. So, basically I can say that this particular signal can even be represented as those boxes. Okay. Now, what happens? At this instant, what is the height of this box? That is actually at that time instant, whatever sample value I get. So, that must be at, suppose this is Tk value, at Tk whatever message signal I get, whatever sample value I get. And in Fm what we will be doing? We will be actually picking those samples, and with those samples we will be generating a frequency, right. That is exactly what Fm is. So, general Fm says that you take every sample and start creating the corresponding frequencies, but we are saying because the message can be only represented by these samples faithfully. So, I will take that sample, and for that amount of period we will keep the frequency same, which is determined by this mtk, right. So, at that mtk what will be the instantaneous frequency? Omega I, that should be, because it is frequency, so it should be omega c plus kf into mtk. This is what we have said already for Fm, that at any time whatever the message signal, it should be proportional, the instantaneous frequency should be proportional to that. That is what we are doing, and that kf is the proportionality constant according to our Fm definition. So, at this instant I will be just creating a frequency which is exactly this, and because I have represented this as a box signal, so that means for this duration the signal strength remains mtk. So, therefore, the frequency will remain mtk. So, I can now say that this entire signal, if I do a modulation, this will just be a pulse over which duration this frequency should prevail. So, the frequency of that should be this. Next time whenever I put, I will have a changed frequency which will be at that instance whatever mtk value will be, that particular one. So, accordingly I can represent the Fm modulation. So, I can just subdivide it into those pulse and modulate that with the frequency that comes out from here at that instance whatever value I get, right. So, this is a faithful representation of Fm modulation, I can immediately say from the way we are constructing it. The advantage we get is now we actually have a pulse which is getting modulated at a frequency which is known to me. Okay. So, how that pulse will be represented in, suppose I want to see the frequency domain representation. So, what will happen? This particular pulse, what is that? That is a unit pulse. Okay. If I go to frequency domain, how that will look like? That will be a sinc function. If 1 by 2b is the width of that pulse because of that sampling theorem, so what will happen? This 1 by that should be the point where it will be cutting, means the frequency axis in the positive half, as well as minus of 1 by that should be the frequency axis where it will be cutting in the frequency axis. Okay. If I take it to omega, that should be 2 pi into that. So 1 by 2b should be 2b into 2 pi, that should be our that 4 pi b. So I can represent this as a sinc function where this point is 4 pi b if I put it in omega, right. But what is happening, that particular pulse is getting amplitude modulated, it is a pulse and then I am modulating it with a sinusoidal, right, of frequency this. So immediately this will be shifted, modulation means it is that pulse getting shifted in the frequency domain to this particular frequency. So correspondingly, if I start drawing the frequency domain chart, I will see for this mtk what will be the frequency, that should be omega c plus kf into mtk. At that center frequency there will be a pulse, there will be a sinc function which is having a, this 0 crossing will be plus 4 pi b. So omega c plus kf mtk plus 4 pi b. What is the maximum that I can get over this center frequency? That should be the maximum voltage that the signal can get, let us call that as MP, and the maximum or the minimum voltage that I get, let us call that minus MP. So it just swings, the overall signal just swings up to a maximum of MP and minimum of minus MP. If that is the case, this entire frequency domain will be populated with so many of this sinc function. At every impulse I will be getting a corresponding sinc function, right. But the sinc function, the maximum that I can get will be populated at omega c plus kf mp, it will not go beyond this, and the minimum that I will get, that should be at omega c minus kf into mp, it cannot be anything less than this, and then there will be a sinc on top of this. Here it is 4 pi b and there will be a sinc on top of this, this is 4 pi b. So overall this variation where the meaningful bandwidth will be, because beyond this the sinc will be diminishing, all the sincs will be diminishing, right, beyond this point. So I can say this is probably my valid bandwidth, and what that is actually this minus this. So that should be 2 into kf into mp plus in this side 4 pi b and this side 4 pi b. So it should be 8 pi b, that should be the bandwidth, sorry, B Fm, bandwidth of Fm. Intuitively this makes sense, right. So you can see that in Fm bandwidth there is a term called this, which is particularly dependent on the maximum signal strength as well as the kf value that you supply, plus there is this 8 pi b where b is the message signals bandwidth. Okay. So these two terms actually comes into picture whenever we try to calculate the Fm bandwidth. Okay. Now let us try to see what this means. Okay. So this is actually what is the maximum deviation in frequency I can get in Fm. What do I mean by that? So my maximum signal is MP, kf into MP is the maximum angular frequency that I can create, and the minimum angular frequency that I can create around omega c, that should be minus MP into kf, right, because the minimum signal will be minus MP. So this is the deviation between the maximum frequency and minimum frequency that I get, okay, in omega. So if I wish to represent it in frequency domain or del f, that must be divided by 2 pi. So this is the frequency deviation that happens due to my signal variation. As you can see, that is directly dependent on this kf factor. So more kf I put, probably there will be more frequency deviation. Lesser kf I put, there will be lesser frequency deviation, right. And immediately what do I get? That should be 2 kf mp divided by 2 pi, right. That is my del f. And the Fm bandwidth now I can represent with respect to this del f. So, kf into mp, that is actually pi into del f, I can write it this way. Okay. So, immediately I can write this kf into mp, that is actually pi into del f. So, therefore, this Bfm, which was earlier derived as 2 kf into mp plus 8 pi b, that I can write as 2 pi del f plus 8 pi b, or 2 pi I can take common del f plus 4 b. Okay. So, this beta Fm was in omega domain. If I wish to get that Fm frequency band in f domain, so I have to divide by 2 pi. So, this Bfm in frequency domain, let us call that f, that should be del f plus 4b. This is the fundamental relation that we are getting, that Fm frequency is due to this frequency deviation that is happening, okay, and the 4b, which is particularly the bandwidth, means related to the bandwidth of the message signal. Initially, you know what happened, people were mistaken that in Fm the frequency terms are getting populated just because I am varying the frequency. Okay. So, that because of that frequency deviation. So, they were thinking that just those frequency terms will capture my bandwidth, because every frequency will have a deviation, sorry, every amplitude will have a deviation. So, maximum amplitude I can calculate, and from there I can get the overall deviation, which is del f. So, if I make del f tends to 0, then my Fm modulated signal also will have 0 frequency band or tends to 0 frequency. This was the initial understanding of people. They were thinking just this del f, if I can capture the bandwidth, that will be the Fm bandwidth. So, initially before understanding all these maths, people were thinking that it is Fm means for different frequency I actually give a different sinusoidal. So, if I can capture this entire del f variation, that must be all those sinusoidal will be populated over there. So, that must be my overall bandwidth. So, if I can make my del f literally very small, which is called the narrowband Fm, we will demonstrate that part also. So, which is called the narrowband Fm. So, if I can make this del f infinitesimally small by just making kf very small. So, if I just do kf very small, whatever, no matter whatever the message signal variation, it will be bounded, and if the kf is very small, this del f will be very small, because del f is just kf into, this del f is kf into mp divided by pi. So, if that is the case, I can always make this very small, and the corresponding bandwidth of Fm will be infinitesimally small. So, that was the initial understanding. People were thinking and propagating this news that okay, Fm will be the savior in terms of bandwidth, because we get a modulation scheme where the bandwidth becomes vanishingly small. But this is not true, that we have understood already, that whatever I do, I can make del f tends to 0, but this 4b will be there. Okay. And then people started trying to see what will happen if we have a narrowband version of this. So, in the next class what we will try to do is, we will try to see if I do a narrowband version of this, what do I get out of this, and then will this formula be faithful, because this formula was derived in an ad hoc manner. You have seen that already. So, it had some intuition, but we are not exactly calculating, because at every value there will be a sinc function, and then how the sinc function dies, what will be the overall bandwidth. We are just saying that wherever the last sinc function goes to 0, that is my bandwidth. That is a very ad hoc way of saying bandwidth or defining bandwidth. So, we would like to see little more insight into that and try to give some intuitive understanding about this formula, the corrected version of this formula, and you will see later on we will prove that that was thanks to Carson's formula. This is actually del f plus 2b, it is not just 4b. We will see that correction also, that comes from tone modulation. So, we will try to capture that part and try to solve the FM bandwidth, means whatever jinx they had at that time. Okay. Thank you.